Hello everybody. For this video, let's talk about inverse trigonometric functions. After defining the entirety of the domain of our basic trig functions, we want to somehow come up with an inverse function, right? That's always been the idea of function. Whenever we learn a new function, we hope to come up with a way to reverse engineer some of these functions. The problem here is we can see that from our definition of trig functions, every time you have a coterminal angle, your trig function is going to give you the same output. This is a pretty bad problem because that just means no trig functions are ever going to be one-to-one. Just because you always have an infinite amount of coterminal angles that have the same output. This type of functions collectively are called a periodic functions, basically because they start to repeat itself after a certain period of time, okay, or a period. By definition, if f of x equal to f of x plus p, this right here is really just a horizontal shift. It does say plus p in this case, that means a horizontal shift to the left, but this p value really doesn't have to be positive, so it doesn't matter whether it's shifting left or right, this just indicates a shift. What this means here is that if you pick up the function and move it over a certain period, a certain number, the function looks exactly the same. That's just another way of saying, again, the function repeats itself after a certain period. So for all of the trig functions, we know it will guarantee to repeat itself after 2 pi, just because after 2 pi, we have a coterminal angles. Every 2 pi, we have a different coterminal angles, and all those coterminal angles are going to give you the same output. It doesn't mean that the trig function require the entirety of 2 pi to repeat itself. Similar to if you look at the clock, it doesn't take 24 hours for the clock to repeat itself. It only takes 12. And so for some trig functions, it only takes half of that 2 pi, which is a pi, to repeat itself. But all these are details I will discuss in the future. So for now, just understand the fact that our trig functions are periodic. They repeat itself after so often. Therefore, we don't have one-to-one. Luckily for us, though, we have a way to handle functions that are not one-to-one. And the way we do that is by cutting its domain, right? We form a restrictive domain, so then we do have one-to-one. Now, this is going to be a little bit of a spoiler, but I want to show you what that looks like. So if you go ahead and click on this link, it will send you to a bunch of the graph and, the restriction domain for these graphs, even though we don't have the graph yet technically, but we'll see these in the future anyways. So a little spoiler alert, let's take a look. This right here is the graph for sine. It's this sine curve, and we can see that it's just the same curve repeated over and over again. In fact, if I zoom out real quickly, you see that it's just gonna look like that over and over and over again. Okay, it's just gonna repeat itself over and over and over again. The one thing that we do already know is that the sine function is going to be between 1 and -1. As you can see, as soon as I zoom in enough, we can see the 1 and -1, that is being the very top and the very bottom of the graph. But this is something that we know already. But when it comes to restriction of the domain, we want to restrict a portion of the domain that's going to make the graph one-to-one while keep as much, preferably all, of the range of the function. And for the sine function, we are basically choosing the very middle portion of the sine function, but a very tiny bit. Okay, so that portion is the one that we're going to choose. Let's just see it by itself. So this tiny portion of the function is how we're going to restrict our domain. So we literally went from a infinite domain for sine into a very restrictive domain from -pi/2 to pi/2. And if you go ahead and click on this link that I provided, then you will have all of the trig function graph and its corresponding restriction on the graph. That is where all of these coming from. Okay, now the choice of these are essentially just a choice. All we need to do is to pick a range, I should say interval. I should not use the word range interchangeably here, but we want to pick an interval or a collection, even though intervals in these cases, where the function is one-to-one, but it has all of the possible range of the corresponding function. Well, this choice is almost entirely arbitrary, almost in the sense that, well, the one that we choose here in the table is the best ones, makes the sign easier, makes the number a little bit easier. Especially these two, the choices were made to uh, follow and to be um, is to be the same choice as the calculus class. Okay, so we'll again talk about more of these choices later on in the later sections, but for now, just take my word for it. Okay, and by the way, you will obviously see this exact choice in your Calc 1 course as well. So, we want to be consistent with the two classes. Okay, and as you can see, the range of these trig functions remain the same. So that's the whole goal, right? That's the whole point. Now, that is the biggest problem that we need to handle, because now that we've talked about this, right, now that we're working with the restricted domain, then we can talk about the inverse. And the notation for the inverse, while it follows the same pattern here, is either this inverse notation, this -1, right, or the arc notation. So it's either this inverse notation or the arc notation. Both of these are interchangeable and they mean exactly the same thing. So if we do have these correct restricted domain, then what we have here is the corresponding trig function and its own inverses. So sine corresponding to the sine inverse and arc sine, cosecant, right, with the inverse cosecant inverse and arc cosecant. All of these terminologies are used interchangeable in basically every book that I have ever used. So you have to know both. Okay, you have to know both of these notations. And we're going to use these interchangeable in this class as well. The pros and cons of these is this one is kind of simple. Is just the con just is so long, right? Arc sine is at this point it's like a whole word, so that is kind of long. Now the pro in some sense is that it kind of reminds you of what's happening. It's working with an arc. I'll mention that in just a hot second. On the other hand, this inverse notation, that is potentially a little misleading. And the reason for that is because a notation we've seen already, where we have, say, sine square x, right? This is just another simplified way of saying sine of x quantity squared. And because I don't want to do double brackets, parentheses all the time, this notation is much simpler, where I put that 2 right in the middle of the abbreviation for sine and the variable choice. Okay, this is especially important later on if you are working with a bunch of different very power of trig functions, and especially if you want to eventually, make your notation a little bit better in dropping the parentheses if you can, and have sine square x like this, then it's definitely essential for you to remember this notation, right? Because otherwise, if you want to think about sine of x squared like that, that means something entirely different. So these are not the same. Anyway, so we know this notation, but the problem is this inverse notation. Well, that looks like sine inverse of x by similar logic, and I've seen this many, many times where people write this as sine of x -1, And we know what -1 power means. It just means bring that to the denominator, right? With the same positive power. But here 1 over sine is cosecant. And believe it or not, I've seen this way more than I would like to admit in the middle of an exam, in the middle of classes where there shouldn't be an issue, but here we are, right? Make sure you do not make this mistake. Inverse trig functions and trig functions are not the same. They're not in the same category of functions, okay? So basically, what I'm trying to say here is that this notation, sine of, let's say, n of x equals to sine of x quantity to the power of n. This is true for n not equal to -1. Okay, so the easier way to think about this is to basically recognize that that -1 is really not a -1, is a abbreviation for the word inverse. Okay, abbreviation for the word inverse. Okay, that's probably going to kind of save you from making this kind of silly little mistakes in the future. Now, you might think this is funny now, you might laugh at this now, but I promise you I've seen this way more often than, again, I like to admit. So please, please be careful to not make this mistake. Okay? Now, back into the definition here. What I like to do purposely here is to align my letters essentially, right? I'm purposely aligning my data here just to show you that we're moving the trig function to the other side. Okay, the way we want to think about this though is that we know trig functions input angles, right? That's why it's theta, and outputs a length, maybe a ratio of lengths, but a length nonetheless. Okay, we can kind of use this idea to be sure that we're working with the right type of function. Because if you look at this, when we move the sign to the other side by changing it to an inverse, we're essentially saying, hey, look, this inverse function now inputs a length and output an angle. They input a length and output an angle. Maybe I should write it this way. Huh? Okay, and this relationship is exactly what tells you that they are in fact inverses of each other. Okay, and the same pattern holds for all 6 trigonometric functions and their corresponding inverses, though once you remember one, the rest kind of follow along, so it's not really too bad to work with these. Okay, once you get used to it, they're not too bad. Now, let's take a look at some quick example here. For this problem, we want to use the definition of trigonometric functions, inverse trigonometric functions, to write theta as a function of x. In other words, here I want to relate theta and x together, but I want to have theta by itself. Okay, so looking at part A here, I have this big old triangle. This is my theta, and what I'm given is the adjacent side of theta and the hypotenuse of this triangle. So what I can do is immediately relate these together using a trig function. Because I was given adjacent and hypotenuse, I can either use cosine or secant. Let's just run with cosine. So cosine theta equals to, and it's just going to be equaling to a ratio, namely the adjacent over hypotenuse. Okay. So at this point, all we need to do is leverage the inverse trig function definition right here for cosine. And what I like to do, again, I like to align my theta and then think to myself, I'm going to move the cosine, the trig function, to the other side by treating it with a cosine inverse. Okay? And then the input remains as the input, so 2x plus 1 all over 11. So that doesn't change, that, just literally copy and paste. Okay, so now I have this, I have theta written as a expression of x. Okay, now it's the same idea if you go ahead and use secant, it basically comes out the same way. So secant theta equals to hypotenuse over adjacent, so 2x plus 1. And at this point, hit it with the inverse, we have theta equals to secant inverse of 11 over 2x plus 1. Okay, so both of these is going to give you the same result. And feel free to use whichever one you want. Okay. Well, next example, very similar. Here, I'm given data, and the two sides I'm given is the opposite side of data and the adjacent side of data. So I still have two choices here. You could just run with one. You don't have to do both of these. Let's just go with tangent. So tangent data, this is equal to opposite over adjacent. Okay, and from here we go ahead and hit it with the inverse function to the other side. Theta equals to, just for the sake of getting used to it, I'm going to use arc notation here. Arc tangent 8 over x minus 1. Again, I'm only using the arc notation here just so I can get you comfortable with both notations. Feel free to use the inverse notation just the same. Okay, so that is the answer for both of these. Really not too bad. It just gave you some practice on rewriting your trig functions basically as a using inverse trig functions. Okay. Well, we also talked about the relationship of the domain and range of function and its inverse. Basically, we're just going to flip the domain and the range of the original function, right? Sometimes even a restricted domain and range. That flip is going to create the domain and the range of the inverse function. So we see that the domain of the restricted sign was negative pi over 2 to pi over 2, and the range is negative 1 to 1. So when we flip that, the negative 1 to 1 becomes the domain of sine inverse, and the range becomes negative pi over 2 to pi over 2. Now, the issue with these range is that if you have to remember all these range, it could be a little bit more tedious. Now, as you practice this problem more and more, you will have no problem remembering these. But for me, it's easier to kind of remember the quadrant of this range. So, for example, the negative pi over 2 to pi over 2, this is really just talking about quadrant 1 and uh, quadrant 4. Okay, the reason for that is because negative pi over 2 to 0, that right there is quadrant 4. 0 to pi over 2, that is quadrant 1. So this really just gives you a range from quadrant 1 to quadrant 4. And all of these might be easier if you just remember the quadrant. So for cosine inverse, it's going to be quadrant 1 and quadrant 2. Right, from 0 to pi is quadrant 1 and quadrant 2. So for tangent is going to quadrant 1 and quadrant 4 again. It's the same quadrant except for we're no longer including the negative pi over 2 to pi over 2. And that's really because tangent at this point has asymptotes at negative pi over 2 and pi over 2. Again, you'll see that in the future, or you can look at a spoiler as I given to you above. Cosecant and secant inverse, this one is a little bit trickier. And again, we pick these ones specifically to be consistent with the one material. And conceptually, it will make the number of choice a little bit easier. Um, but at this point, you just have to take my word for it. 0 to pi over 2, again, that's in quadrant 1. Pi to 3 pi over 2, this is actually in quadrant 3. Okay. Same thing with secant inverse, same idea, quadrant 1 and quadrant 3. Okay. And finally, going back to cotangent inverse, is going from 0 to pi, which is quadrant 1 and quadrant 2 again. Okay. Now again, even though in terms of just quadrants, right, we have similarities. So cosecant inverse and secant inverse were quadrant 1 and quadrant 3. And sine inverse and tangent inverse are the same quadrants, and cosine inverse and cotangent inverse, right? They have the same quadrants. However, if you kind of compare these, they are still slightly different, right? Like I said, you have to kind of treat them all a little bit differently. Okay, well, let's practice that a little bit. We're going to do the next problem in two different ways here. For sine inverse, okay, for sine inverse, let's stick with this. How do we tackle this type of problem? We'll have slightly bit more efficient ways in the future, but for now we have to kind of go around and revert back to the definition. We just learned about sine inverse. Might not be very familiar with this, but I know sine inverse inputs a length or ratio of lengths, if you will, and outputs an angle. So I know this is supposed to equal some angle. Let's call it theta. What I'm doing here is to write this out as an equation, because what that does is to allow me to bring this back into the trig function by definition. This means square root of 2 over 2, this is equal to sine of theta. And once I bring it back into the trig function, this is something that we're kind of familiar with. So I can find out a value of theta where sine theta is equal to radical 2 over 2. And if you remember either the chart or the finger trick, we know that sine of pi over 4, or 45 degrees if you want, is equal to radical 2 over 2. Okay? Well, therefore, theta is equal to pi over 4. Well, close. In fact, this would have been the answer, and this is the right answer, but we can't quite make that decision just yet. Okay, we can't make this decision just yet. And the reason for that is there's another one of these. There's another one of these angles where sine of pi over 4 is equal to radical 2 over 2. And that answer is actually 3 pi over 4. So what is happening here? Well, if we take a look at all students take calculus, they take a look at all students take calculus, we know that sine is positive in quadrant 1, of course, but also in quadrant 2. So we know there is an angle in quadrant 2 where sine of 3 pi over 4, sine of theta, is also going to equal to square root of 2 over 2. So the way we find this is that the quadrant 2 angle have a reference angle of pi over 4, right? Because we're saying quadrant 2, sine has also positive values. So what we're really saying here is theta is equal to, the formula in quadrant 2, by the way, is pi minus theta bar equals to pi minus theta. And what that means here is is the theta bar is my reference angle, which is pi over 4, equals to pi minus theta. And from here, we can easily calculate theta. essentially by kind of swapping these two. Uh, by swapping these two. And what we're going to get here is theta equals to pi minus pi over 4, which is 3 pi over 4. Okay, so that's where I get that 3 pi over 4 from. And from here, we know that sine of 3 pi over 4 also equal to radical 2 over 2. So that is kind of a problem because now we have to make a choice. And choices, while sometimes are easy to make, other times it leads to inconsistency. So we don't always like choices. Okay, we don't always like choices. See, this is where the range of the trig inverse function comes in. Because now I actually have two choices. The question is, do I want to choose this or do I want to choose 3 pi over 4? Well, we know, though, that the range of the sine inverse function is from negative radical pi over 2 to pi over 2, which again is in quadrant 1 and quadrant 4. So all you're really asking yourself is which one of these come from quadrant 1 or quadrant 4? Well, we know this one came from quadrant 1, this one came from quadrant 2, so therefore this is the answer. Okay, therefore this is the answer. Okay, so even though we got this one first, it's not necessarily guaranteed that is the answer. We have to make a basically a double check, right, to make sure that it is in fact the answer. Okay, so that's the bit that is a little bit more tedious, but you kind of have to do this at this stage of the game. Again, I promise you, it does get a little bit easier in the future, but for now, you kind of have to stick with this. Uh, although there is a slightly different method following the same logic, but I'll go ahead and show you and see which one you like more. Well, let's talk about this cosine inverse. Same idea here. You go ahead and let that be theta. And then by definition, what we're saying here is negative radical 3 over 2 equals to cosine of theta. So bring everything back into, something that I'm already familiar with is basically always a good step. So the way we're going to tackle this is to jump into all student take calculus right away to figure out uh, my quadrant for theta. Okay, so in the previous step, we kind of figured this out afterwards, right? We kind of used the quadrants afterwards. But now let's just use it right away. We have actually two pieces of information already. So I can already talk about all student take calculus here. And the two piece of information is one, cosine inverse has a range from quadrant 1 and quadrant 2. So I can already use that to identify quadrant 1 and quadrant 2. Okay. On the other hand, what I have here, this equation here, really tells me that cosine is supposed to be negative. Well, cosine is negative, not in quadrant 1, not in quadrant 4, so it has to be in quadrant 2 and quadrant 3. Now, as soon as I have both of these information written down, I know the interval that I'm working with is this overlapping interval, which is quadrant 2. Once I know that my theta is in quadrant 2. Therefore, going back to the same reasoning as before, cosine of theta is, well, cosine theta should be negative. That's part of the given. But the theta can be calculated using the reference angle. Turns out in this case, the reference angle because it's the same quadrant, follows the same formula. The reference angle is equal to pi minus theta. Okay. Now we want to know what reference angle we're actually working with. And we know that reference angle of the trig functions are always going to be positive. So we know that cosine of theta bar is equal to positive radical 3 over 2. And from here, cosine of what equal to radical 3 over 2? Well, again, the table or the finger gesture here, we know that this is going to be pi over 6. Okay, which means my reference angle is equal to pi over 6. So plug that into the formula, pi over 6 equals to pi minus theta. And again, similar trick as before, I'm just going to go ahead and flip these. And theta is therefore equal to pi minus pi over 6. And if you make common denominator, you can get the result equals to 5 pi over 6. Okay, so that is the right answer for here. We have theta is equal to 5 pi over 6. All right. Slightly different approach for both of these problems, but both of which is really leveraging the same idea. Because at this point, this is all we got, right? We have the definition, we have Gauss-Unit calculus, we have reference angle, but aside from that, we're limited by the technology of our time, if you will. All right. Now, working on this problem, we kind of see a very important issue, and this is going to be an issue that is going to fundamentally change how we view our answers in the future, which is the idea that a trig inverse function, because it is a function, one input gave me exactly one output. Same thing here. One input gave me exactly one output. That's just the very definition of functions. However, if we revert from the inverse trig function back into the trig function, right? This is a basic trig equation. Well, these trigonometric equations always have multiple answers because our functions are periodic. There's always multiple answers, right? Our function is not one-to-one. Even on the interval of 0 to 360 degrees or 0 to 2 pi, our trig functions are not one-to-one. Therefore, there's likely multiple answers. In fact, you all know by now that our functions are periodic. Therefore, it's always going to be infinite to 1. Therefore, there's always going to be infinite amount of answers as soon as you get 1. So later on, we're going to have a whole section dedicated to evaluating equations like this, in which you're always going to have infinite amount of answers. But luckily for you guys, that's a story for the future. Okay. For now, let's go ahead and work with a little bit of calculator work. The idea here is we want to solve for these basic trigonometric equations, but we also want to be able to get all of the answers instead of just the calculator answers. Okay? And for this kind of question, you should be careful about the type of units in your calculator, whether you're working with degree or radian, just because here we actually have to put inverse trig function within the calculator. Okay, so for example, here sine theta equals to negative 0.47. We can easily get our first answer because by definition, theta is equal to sine inverse of negative 0.47. Okay, now because this trig inverse function is going to spit out some angles, the unit of this angle is going to matter. okay? So if I punch in sine inverse of negative 0.47, the answer I'm going to get is approximately negative 28.03 0.034 thousandths. A number this quote unquote big, 28, this basically have to be in degrees. Okay? Because if you think about it, radian answers are actually really small because 2 pi is just 2 times 3.14. It's actually just 6 something. Okay, so 28 is huge in that respect. Anyways, so we got our first answer, and you can see that, that is just going clockwise, right? Because it's negative, going clockwise by 28 degrees. Okay, going clockwise. Here, maybe I'll label it negative here just to be consistent. But we know negative just means rotating clockwise. Okay. Now, this is a quadrant 4 answer, as we can see it. What that means here is I have a quadrant 3 answer that I'm supposed to get. And the way we kind of think about this is that if theta 1 is our first answer, is going to be a negative angle, that means I'm rotating clockwise. Well, when I mirror to the left-hand side, right, mirror to the quadrant 3, I'm actually going to start at pi and rotate now counterclockwise. You see, this is why it is negative theta 1. But again, I'm starting at pi instead of starting at 0. But now we can see that theta 2, our quote-unquote second answer, is a supplementary angle to negative theta 1. Okay? In other words, we can find theta 2 by simply taking pi and subtract theta 1. Oops. Actually, let's not use pi because what? Because we're working with degrees, so let's be consistent and do 180 degrees minus theta 1, or I'll just put theta here. Okay? And theta, or theta 1, is already negative 28.034 degree. That just means I'm just doing 180 minus, or minus negative, right? So that's 180 plus 28.034. Okay, so let's do 180 degree minus theta 1 is negative 28.034 degree. And of course, double negative give you a positive. So the answer here is just going to be 208.034 degree. Okay, so my second answer can be found this way. Now you should always double check. When I say double check, I mean plug that number, that result, into the calculator. Okay, go ahead and try that on your own. But if you did it, then sine of 208.034 degree. This is approximately, I'll write a few more digits than necessary, but on the calculator, it shows to me as 0.469994. And you can see that is really close to negative 0.47, right? Please don't write a degree. This is not a degree, right? But this is really close to 0.47. And of course, that's because that is the second answer, okay, for this trig equation. Okay. Now, that's the method for sine. For cosine, it's a little bit different. just because the symmetry is a little bit different. Let's take a look. Same idea. We can get the first answer by doing theta equals to cosine inverse of 0.65 and punch that into the calculator. We're going to get 49 point, let's say 458 degree, again in the nearest thousands place. Now this one is a little bit different because if you think about this way, right, theta 1 here, let's just label that here again, 49.458 degree. This is a positive angle. That means I am going clockwise here. And we can see because cosine is reflexive up and down, right, top to bottom, all we have to do is make a reflection on the bottom. So negative theta 1 here will be negative 49.458. And the way we think about that is that theta 2 and negative theta 1 combine together to be 360 degrees. Therefore, theta 2 is equal to 360 degree minus theta 1, or theta. That's my notation. Therefore, we have 360 degree minus 49.458 degree. And of course, punch that into the calculator. I have 310.542 degree. Okay, always a good idea to double check. So if I do cosine of 310.542 degree, this is approximately equal to, just because I have rounding error, and I'll write quite a few more digits just to make my point here, 0.650005 3. Okay, which, like I said, is very, very close to 0.65, just like how we see it before. Okay, so that's how you get both answers within the range from 0 to 300 degree, 360 degree, or 0 to 2 pi, right? Again, if you're using radians, by using calculator. Okay? So sine, cosine follows a slightly different formula.